Hello, this is the fourth video on the same series. I wanted to mention something I forgot to mention at the end of the last video. We're talking a little bit about this equation in the last one, and I promised that I would talk more about this one later. And there will be a separate video on just examples of how to use that. But an important idea I forgot to mention was that if you look at this equation, it says that the pressure at a certain depth, h, is equal to the depth itself times the density of the liquid times g, the gravitational acceleration, or 10 meters per second squared. There's nothing there about the cross section of the cylinder or the or the container, so or the amount of water in terms of the width of it. So that means that if I had a container like this compared with one like this one, and you compare the pressure at this point with the pressure at this point, where this is the same H, it doesn't matter if this has a lot more water in it because it's a wider cross section than this one. Doesn't matter, what matters is the H, so I will get the same pressure here as I will get here. Okay, that's really important. Some questions try to trick you with that and ask you to see if you understand that. So it's independent, it just matters the depth. It's independent from the surface area. And so remembering what we said before, the pressure would act in all directions equally at this point, right? And the same thing here, in all directions, because of the Brownian motion, all the random direction of all the particles that are exerting that pressure. But the actual pressure level itself, the amount itself of pressure, would be different from, say, this other height. Okay, but if they are at the same depth here and there, the pressure would be the same. Alright, so far we've talked about, in these videos, we've talked about the ideas of density. We talked about measuring volumes of irregular solids, talked about pressure and fluid pressure, and so we looked at the formula for density and the formula for pressure. And I would like to talk a little bit now about, actually Brownian motion we already covered, so I can cross this one out, in the sense that we've already talked about it in the third video, in the last one before this one. And changes of state is what I wanted to look at now, and Kelvin temperatures also. I think we should have enough to talk about both of them, and then move on to the last video where we talk about the pressure law and Boyle's law. So let's find some space to talk about changes of state and what we mean by that, and this should be fine. So let's have a look at what we mean by changes of state. Changes of state. So you should know that state comes in matter comes in three main formats: solids, liquids, and gases. There's also a fourth state called plasmas, but we don't do it in GCSE. Solids, liquids, and gases, and you can go from one state to the other by supplying energy to a substance, and you change the configuration of the way that the atoms are related to each other, and therefore you go from one state to another. So what happens if you say, this is the temperature of the substance that you're measuring in degrees C, and this could be, let me just draw that properly, temperature in degrees C, and here you have heat that you're supplying heat energy to the substance. Okay, and heat and temperature are not the same thing. Heat can contribute to temperature, but they're not exactly the same thing. For example, I can give a lot of heat, right, with a fire for a long time to an ocean of water or a lake of water, or a really big amount of substance, and even though I'm applying a lot of heat to it, the temperature might only go up by fractions of a degree, right? So the temperature has to do with how much matter there is there, and the capacity that the substance has to absorb matter is not that the heat immediately gives you temperature. And equally, if you give that same amount of heat to a much smaller amount of matter, the temperature might rocket and get really, really high. So heat is just energy that you give to the material, and temperature is the temperature of it. It's a measure of the average kinetic energy of the molecules in there. But if there are a lot of molecules, then that heat energy is going to be spread between them, and so on average they won't all have a lot of energy. So in other words, they won't have a high temperature. So the idea of heat and the idea of temperature are related, but not the same thing. And so I can have a substance at a certain temperature, and what we've noticed when we do that, as we start adding heat, is that this happens, and then suddenly there is this stage flat, and then it goes up again. So the amount of temperature goes up, and then again flat, and then it goes up again. So why this behavior of steps, and where is each state of these three, what do these correspond to on the graphs, and let's get some understanding from what's happening here. That's all very important. So what are materials when they're colder? What happens when you cool materials, or when they're just in their natural state, depending on what material it is? Well, this section here is for a solid. It's when they're cold, materials like to be solid, because the particles are the closest together and they're not moving too fast, so they tend to have very strong bonds between them, and they form these close packed structures which tend to be solid. That's why when you get liquid water and you cool it, you get ice. As you start to heat it, suddenly you reach this point where what's happening here in this flat line? Well, you're still increasing the heat, because as you progress on this axis, it means that you're adding more heat. But for some reason, the temperature of the material, even though you're adding more and more heat, the temperature is staying the same. So there must be something happening with that energy that isn't going into the kinetic energy of the materials. So before I talk about that, let me then say, well, what's happening between here and there? So this is really, we call this liquid. And finally, when you get to this point and you're in this part of the graph, then this is a gas. Okay, so as you heat substance, it goes from a solid to a liquid to a gas, and in the middle there are these transition areas which we need to understand a little bit about. Not very much, just enough to have a sense for what's happening. And in a liquid, you should know already that the particles are spread out further away than in a solid, in most liquids compared with their own particular solids. Water is a slightly strange example, but and in gases the particles are even farther apart, so they have more kinetic energy, and so as we heat a solid, the particles start getting further away from themselves and from each other, and they therefore go into the liquid structure, and then eventually you give them more energy, they leave the liquid surface and they turn into a gas. So what are these flat points in between of what's going on? Well, as you supply heat to a material, you're not only giving kinetic energy to the molecules so that they move faster, you're also overcoming the forces in between the molecules themselves. So these molecules have attractive forces between them, and as you give more and more heat to the particles inside of a material, you're not only giving them energy so that they move quicker like that, you're also overcoming this kind of bond or link between them so that they can be further apart. So you can think of it as giving it potential energy. Like you have a book here on the table and you lift it up, and as you lift it up you're increasing its potential energy, and for that you need to do some work, you need to put some energy into it. Here it's the same, they have an average distance that's quite close together as a solid, and if you now want to increase the average distance between the particles, you need to give it some energy so that they can be further apart, as well as giving them kinetic energy. So what's happening here, and the same here, is that a lot of that heat that's coming in is no longer going into increasing the kinetic energy of the particles, or the temperature in other words. It's going into making them getting them to be further apart. So here it's transitioning from being a solid into being a liquid in this area there. And the same thing is happening here, but from a liquid to a gas. Now the energy is no longer going into increasing the temperature between here and there. The energy is going into separating the molecules more so that they can be a gas, and then from here then the gas is already complete, most of the material is already a gas in this state, and then it starts again to heat up. Once it's a gas, it can't separate anymore. It's not going to change of nature anymore until it reaches plasma, which is way off this temperature scale. And so the new heat that you add starts to increase the temperature of the gas itself. It doesn't change the nature of the substance. Okay, so hopefully that explains why these flat parts are there. And so we need some words to describe what's happening here. So how do we go from a solid to a liquid? So let's choose a different color. To go from a solid to a liquid, what you do is that you melt, right? So that movement is called melting at this point, whilst this movement, which you can do by removing heat from a material, is achieved and it's called freezing, right? And the same thing is happening here, but it's going from liquid to gaseous, so that's called boiling. And if you're going the other way, from a gas to a liquid, it's called condensing. Right? So you say there's condensation when you have droplets of liquid on your window that were, or in a flower in the morning, or in, I don't know. You can get condensation in lots of places where a little water that was previously dissolved, or water vapor, is now cooled down and it's become condensed. That's really what happens a lot with clouds. Really, they're just condensation, and then they just drop, and they can even freeze if it's too cold. It goes from water being water vapor to now water being liquid in droplets in the cloud that don't fall because they're too light to fall, and they collect together. They have affinity between them, and then they start raining. Very often, or in the process, they freeze and they become solid. So now they become crystals of snow, and so they've gone through the whole cycle. Then they might fall onto the floor, and some heat energy comes from the sun, and then they might melt, and you might get a puddle of water. So now you went through from here, from solid back through melting into the next part, which is the liquid, and then that the sun keeps on going, and that could evaporate, and then you get the cloud that goes that forms from the evaporation of the water. So that's the full kind of water cycle in terms of going one way and the other way in this graph, and it can be explained using the average distance between molecules and the temperature given to them by the heat. So hopefully this makes sense in terms of the relationship between solids, liquids and gases, how you go from one to the other, giving heat or removing heat, and how it happens in nature automatically when the heat is received in different amounts during the day, during the afternoon, in different parts of the planet, and so forth, and so on. Okay, so what else is important to talk about here? There is, I'm sure you've heard the ideas of melting points and freezing points and boiling points and all of that. So what are they? Well, if you look at the temperature in this y scale, then the temperature at which this happens is the melting point or the freezing point, depending on what direction you're going, if it's cooling or if it's heating, of that substance. So that would be this temperature, right? Hopefully that makes sense. It corresponds to that flat part. Then the corresponding one up here, where the boiling and the condensation happens, that is the boiling point or condensation point. So this we would call melting point, and this we could call the boiling point of water or whatever it is. And what happens at those points is that you're converting all of the material to the next phase. So either you're going from solid to liquid, or from liquid to gas, or whatever. Excuse me. But it's also possible that at temperatures lower than, for example, the boiling point, so you can have a liquid at this temperature. Okay, you can have a liquid at this temperature here, whatever that temperature is, and you could get some of the molecules in the liquid, or some of the portions of the liquid turning into a gas, and we call that evaporation. So even when the liquid is not at the boiling point, you can still have, so here's the liquid, right? You have a glass of water in the air right now. You will get the situation where some of the particles inside of the water have more energy than others, and they have enough energy to really leave and separate themselves from each other enough to have a bit of water vapor around the liquid. And that will happen at most temperatures, unless you're so cold that this is turning into a solid. That won't happen. But if it's warm enough that this is a normal liquid and in equilibrium with the environment, then there's evaporation happening, and then the opposite happening also. What's the opposite? Well, it's going from gaseous to liquid, so it's called condensation. So that's happening as a dynamic equilibrium between them, and if you start to heat it up, then more of them will leave that will condensate, so then you'll see the level of the liquid to start to fall if you start to heat this up. But if you're at a normal temperature and this is in a dynamic equilibrium, that won't happen, and you'll get roughly as many being evaporated as they're being condensed. Okay, so we call evaporation, we call it the process of going from where material goes from liquid to gaseous, but this is happening below the boiling point. Okay, that's evaporation. If it happens at the boiling point, it's called boiling, and that's when you see the bubbles coming up and it's boiling away the liquid. Hopefully that makes sense. It's an important point about evaporation, right? The seas in the oceans and the rivers and the water on the ground and everything, it evaporates, right? That's how we get clouds. But it does so at a temperature that is lower than the boiling point of water. It's not at 100 degrees, it's happening lower, so at a lower temperature, so that's evaporation. So hopefully that makes sense. So evaporation is a special case of going from liquid to well, it's the most usual case actually, and boiling is a special case that happens at the boiling point temperature. So that's important to say. And the other thing that I wanted to say in this video is the temperature scales. That's important to do. So we have a few minutes, I'll try to stop at 20, a few minutes left. And so what's happening with the temperature scales? Well, normally we do temperature in degrees centigrade, right? But centigrades are a little bit random because they are just based on the freezing point and the boiling points of water. That's what they were. That's how we came up with them, right? So the freezing point of water is around 0 degrees C, and the boiling point of water is around 100 degrees C, and that's how the degrees were designed, so that 100 would be at that temperature and 0 would be at the freezing point of water. But water is not, even though it's a very special substance, it's not particularly. There's no reason why we should base our whole unit for temperature on water, so they came up with a more universal idea, which was cooked up by a guy called Kelvin. Lord Kelvin was one of the most sort of prolific inventors and scientific people of the well, in all time, really, together with the rest of the big names that you probably know about. Kelvin said, well, when since temperature is proportional to kinetic energy, then when the substance has no kinetic energy, that's when we should call the temperature 0. And he came up with this idea of absolute 0, which was the temperature at which the material doesn't have any kinetic energy whatsoever. So we need to know how to convert from degrees Celsius to Kelvin and vice versa the other way around. So I'll do that just here really quickly. It's quite an easy. They figured out that the 0 of temperature in terms of Kelvin happens at minus 273 degrees Celsius. So that if somebody tells you that the temperature in Celsius is 30 degrees C and they want you to write it in Kelvin, then you say, well, 0 Kelvin equals minus 273 degrees Celsius. That means that if I want to be at 0 Celsius, I need to add 273, right? So if I add 273 degrees to this, they both have the same size, both types of degrees. So if I want to ask, well, how many kelvins is 0 degrees C, it's going to be 273 positive Kelvin, right? So if 0 Kelvin is minus 273, then 273 Kelvin will be the equivalent of the 0 degrees Celsius. So if I want to know what 30 degrees Celsius is in Kelvin, I have 273 would be 0 plus another 30, so I have to just add 273 to put it in Kelvin, so I would get 303 Kelvin would be the equivalent to 30 degrees Celsius. Hopefully that makes sense. So again, what about minus 10 degrees Celsius? How much would that be in Kelvin? Well, 0 degrees is plus 273 Kelvin, but this is minus 10, so I gotta take away 10 from here, so my answer then would be 263 Kelvin, right? That would be minus 10 degrees Celsius. Hopefully that makes sense. And the way you go the other way, so if I want to go from 400 Kelvin to degrees Celsius, instead of adding 273 degrees as I've done here, to go from that to the other one, we even in this one where you had the minus 10, we also added 273, but because this is negative, it just comes out to be that much. So whenever you're going from degrees Celsius to Kelvin, you add 273 basically, and when you go from Kelvin to degrees C, you do the opposite, so you subtract 273. So let's see how that works. This is 400 Kelvin, we subtract 273, right? And what's the answer? 128. So 400 Kelvin would be 128 degrees C, right? I've just subtracted 273. Okay, so that's how you go from one to the other. And the meaning of 0 Kelvin and the implications of it, we'll talk a little bit more about when we talk about the pressure law and the volume law, because they have a meaning in terms of 0 Kelvin has a particular meaning in terms of pressure of what's going on. Okay, and they're not drawn like this. It's not degrees Kelvin. You just write write Kelvin. So 30 is just Kelvin. Okay, instead of degrees C, we just write it as K. Okay. All right. So I think we're out of time here. I'll continue talking about the next part in the next video. And we're getting to the end of this series now, where we've talked about the changes of state in this one, and the temperature, the Kelvin temperature, and now we have the pressure law and Boyle's law, and we'll talk a bit more about the Kelvin temperature there, because these are always expressed using Kelvins instead of degrees Celsius. Alright, so hopefully that was helpful.